Okay, so we continue. Sorry for some discussion in Russian. So I'm going to prove theorem 1, and I also want to state an improved version of theorem 3, where this 2.5 is replaced by 2.4 or something. But before I do it, I first prove theorem 1. It's very easy actually. So there are 3 proofs. Let me mention that there are 3 proofs. The first proof is group theoretic, and it actually proves the following lemma. If G is a meta-abelian group, this means that G, the second derived subgroup is trivial. It is so solvable, too solvable, it can be said. And its abelianization is Z, like we have for nodes. Yes, so for nodes the abelianization of the fundamental group is Z, because this is the first homology. Also for wild nodes. Then every 2 elements of this group such that their images are the same in the abelianization are conjugate. Maybe it's better to say that they are conjugate if their images in the abelianization are the same. So it's clear that this lemma implies theorem 1. Yes, so no, it's not clear, but let me I will explain it.
Ну, лемму, наверное, можно проверить. Тем более, что там двойку написали. А как из леммы теоремы следует? Лучше объяснить.
Okay, let me explain how lemma implies theorem.
Формулировка третьей теоремы уже не нужна. И мне, в смысле, если планировали ее стереть.
Maybe I try to keep it, but I can erase this one. So there is another lemma. Let me state it in the form of a picture. So suppose we have an isotopy of a node given an isotopy of a node, and draw this isotopy. So this is S3 times 0 and S3 times 1. Then I claim that it is always possible to choose a finite number of nodes so that we just keep these nodes. We don't move them, but they don't intersect this isotopy. And they are exchanged finitely many times, but there are no conditions about how they are exchanged. The only condition is that they are linked with this isotopy with linking number 1. So, I don't know, this can be called, maybe this isotopy can be called KT, the image of the isotopy, and this can be called Q, Q1, I don't know, times T. Maybe it's better to start from the bottom. This is Q1 times 0 T1. And this is Q2 times T1 T2. This is Q3 times T2 1. So there exist PL knots in the continent, such that okay, so also there exist numbers 0 equals T0 less than T1 and so on, less than Tn, which equals 1. And Qi is disjoint from Kt for all T in the segment from Ti to Ti plus 1. And also to link a number of Qi and, for example, Kt is 1. Okay, now it is stated formally.
Ну это два комардизма. А у вас там
No,
написано...
no, this is not two cobordism because they are exchanged in any way. No restriction on how they are exchanged.
Ну вот link number равен 1, это значит, что вы коммутатор можете.
Yes, yes, this lemma now implies that this will be a two
Не
cobordism.
понял. Написано такое, что U пересекает QT для всех T. Что значит пересекает?
Yes, thank you.
Не пусто или пусто?
Empty.
Это ноль парадизм, да?
Нет, а вот G2 у вас там написано.
So far this is infinity bordism, but
Бесконечность вроде сложнее всех конечных должна быть. По строению просто там чем выше n, тем выше.
yes, you're right. Okay, zero bordism. Yes, zero bordism.
Вот G2 где у вас тут в этом? Как вы там G2 используете, а здесь у вас произвольные какие-то. Вы факторы берете, что ли?
Okay, so let me explain how these two lemmas imply theorem 1. Yes?
В чем утверждение второй lemma?
Given an isotope Kt of a knot, there exist piecewise linear
Простите, я
knots.
думал, это условие.
There exist piecewise linear knots which are disjoint. Each is disjoint for appropriate time.
Ну а на картинке вот Q2 с KT2 равно 1 тоже должно быть там как-то, да? Они там должны цепляться в этом в срезе горизонтальном с этой с Q2 получается, да?
Okay, I think this should be T2. No, T1. T2, T2, T3, T3, 1. Is it better?
Better. Понятно, да.
So, let me explain how the two lemmas imply the theorem. Yes? Can I do it? We just consider, so G, let us fix some level T. And we consider the group. We consider a fundamental group of the complement to KT. But we take the quotient by its second commutator subgroup. And this quotient is metabillion. Yes, Piotr Mikhailovich?
Ну, наверное.
Because it has trivial second derived subgroup. This quotient is Z for the original group, but after you take this quotient and then again take the abelianization, it's the same. You can. It doesn't matter if you abelianize this group or do it after taking this quotient. So the conditions are fulfilled, and then any two elements A, B, which have the same class in the abelianization, are conjugate. But here we look at, so yes, this T should be Ti, and then we have here Qi and Qi minus 1 for this level. And they, well, if we fix some lace point and connect them, then their classes will be conjugate by this level. Their classes will be conjugate modulo second commutator subgroup. But this is what we need for two-wordism. Two-wordism means precisely this, that these classes are conjugate modulo the second commutator subgroup. So two lambdas imply this theorem. Yes?
Ну, вроде да.
But I don't want to prove lambda 1, but I will prove lambda 2. But it is easy to prove lambda 2. So we are given this isotopy. Okay. So let us take any level T. Then for any level T, we can find the knot QT, which is disjoint from KT and has linking number 1 with KT.
That's not okay.
Uh-huh.
So neither can I read lemma 2 because it's too small, and I'm a bit lost what these figures really mean.
Are you okay with the statement of the lemma?
Yeah, so
Or should I repeat the
I
statement?
didn't catch this philosophy of steps. So
So the statement of the lemma is that we can find piecewise linear knots in the complement of this knots KT such that we can exchange them only finitely many times, and they have link number 1 with any of these knots.
what are you exchanging? What are you exchanging?
I am exchanging different PL knots. Both of them lie in the complement to some moment of our isotopy. Maybe let me tell you the proof, and then the statement will be clear from this construction. Okay?
Okay.
Let me draw a new picture. Forget everything that's written there. So we have an isotopy KT. This is an isotopy of possibly wild knots. Now I take some specific value T, and there is this knot KT. So it's KT is just some knot in the 3 sphere, possibly wild. then I claim that there exists a PL node Q T which lies in the complement of KT and such that the linking number of QT and KT equals 1. Okay?
Okay, at least I understand this statement.
Well, if KT is a piecewise linear node, then this is obvious, because you just take some meridian, for example. Yes?
Yeah.
If this is a wild node, then I agree that this is not so obvious, but actually Recancel told us a proof of this theorem in his talk 1 year ago at this seminar. So he actually himself found a good proof, and I found a different proof which is not so good. But it is, in any case, it is more or less an exercise. So, okay, the idea of my proof is to use the Alexander duality. If you have any wild node, you still have, you still have its homology as a circle is still Z, and then the cohomology of the complement is also still Z, and also the homology of the complement is still Z. But if you have homology Z, then you can represent this Z by some number of circles, and then you can take you can, for example, take the connected sum of all of them, and you get your piecewise linear node, which links this wild node with linking number 1.
Okay.
So this is a sketch at least. There are some missing details, but this can be made rigorous. So this is one possible.
Okay, for the moment I'm willing to believe it.
Почему нельзя взять разделяющий диск, там его границу, там
no, this wild node may have no meridians. It's possible that there exists no disk which pierces it in one point. For example, the Binks link is precisely such a node which is not pierced by any disk in any point. So there are some difficulties, but by considering homology, for example, it can be solved with some effort. So actually, well, okay, let me not comment anymore. If you tell me that there are some missing details here, I agree with you. But I also think that everyone believes that this statement is true. Yes? So for any moment of time, we can find a piecewise linear node QT with a complement which links this KT with linking number 1. But then we can find some epsilon such that if we look at KT plus epsilon and also at KT minus epsilon, then they are still disjoint from this QT. And also they have linking number 1 with it. So we can actually take here such a product QT times T plus T minus epsilon, T plus epsilon. And then, so this epsilon depends on T. So let me call it epsilon sub T. Now for every other T we have a different epsilon, but we can look at the unit interval 0, 1. And for each t, we have an open interval from t minus epsilon t to t plus epsilon t. So we have an open cover of our unit interval of our closed unit interval by this open intervals. And there is a finite subcover because the unit interval 0, 1 is compact, closed interval. So we take this finite subcover and we get a sequence of such nodes. So this will be some ti's because we select a finite number of these intervals. So there will be some ti's, t0, tn, and this gives us a sequence of piecewise linear nodes such that we can just exchange them at any point where consecutive intervals intersect. We exchange the node corresponding to the previous interval, we exchange it to the node corresponding to the next interval. And this gives us this picture. And this is actually what we wanted. Namely, we
Okay.
Okay?
Okay, thank you. Now I understood the idea.
Now, if we believe this lemma 1, then theorem 1 will be proved. Because every such exchange, it was an arbitrary exchange. I replaced, I found these two nodes completely randomly. I only know that they have linking number 1 with KT, both of them. But this is enough to apply this lemma. Because I only need here that these two elements A and B have the same image in the abelianization. And I also need to look at a meta-abelian group. And this is achieved by taking the quotient by the second commutator subgroup. And then obtain that these two elements are conjugate. So it means that the elements representing these nodes are conjugate modulo the second commutator subgroup, which is what we wanted. Okay? So modulo lemma 1 we would prove theorem 1. But I don't want to prove lemma 1 because it is a group theoretic proof which is not the shortest one. But there are another two proofs. Modulo theoretic and geometric.
Модули, это модули находятся.
I want to tell you these two proofs instead of the first one. The first one, actually the idea of proof of this lemma, or the way I proved it, was the following. I just looked in the internet and I found that the conjugacy problem for meta-abelian groups is solvable in the sense that there is an algorithm to solve the conjugacy problem, to determine if two given elements of a meta-abelian group are conjugate. And then I just looked at this proof and found proved this lemma 1. But it is a little bit long, but the other two proofs are short. So Petr Mikhailovich has no chance to hear the short proofs. So let me tell you proof number 2. What is going to be the module? Of course, we want to look at G prime. So G, okay, now G will be not this quotient, but but just a fundamental group of the complement to KT. So it can be called GT, but let me fix T and just call it G. So G prime modulo G double prime is the same as H1 of the universal of the infinite cyclic cover of X. Okay, maybe I should write S3 minus KT and the infinite cyclic cover. So what is the infinite cyclic cover? We have our wild knot, and there is a map from its complement into S1, which is given by the generator of the cohomology. So again, the cohomology S3 minus KT is Z by the Alexander duality, and the generator of this group gives us such a map, because this cohomology group is isomorphic to the set of homotopic classes from this into S1. S1 is a Eilenberg-MacLane space KZ1. So I get this map into the circle, and there is, over the circle, there is the universal cover, the real line. And I take the pullback from R, and this will be this infinite cyclic cover, which is written here. So, by this construction, the fundamental group of this infinite cyclic cover is the commutator subgroup G prime. G was this fundamental group. Well, because this map into S1 induces the map into Z, which is the abelianization. And this cover really corresponds to the kernel of this abelianization map. It is another way to define this infinite cyclic cover. And the kernel of the abelianization map is the commutator subgroup. So the fundamental group of this covering space is the commutator subgroup. But when we take the quotient by the commutator subgroup of this commutator subgroup, if G prime prime is G prime and then prime. So this quotient is the abelianization of this, and the abelianization is the first homology. So we have this isomorphism. And there is an action of Z. So both of these abelian groups are modules over the rank normals. So what is well, the action of this Z is just by multiplying. We can multiplying cycle by an integer. We again get a cycle. And here we can multiply any element of an abelian group by an integer. We again get an element of this abelian group. What is the action of T? So geometrically, it is just a deck transformation group of the covering. The generator of the deck transformation group. The deck transformation group is that, and T is its generator. And algebraically the action by t is conjugation. So,
Простите, вы сейчас произносили фразу что-то за transformation.
так,
Группа преобразования циклического накрытия. Да?
Что значит так?
ну это группа послойных, как это называется, как вы сказали, Никита?
Группа преобразования накрытия.
Группа послойных преобразований.
Это не, может, автоморфизм?
Автоморфизм, да.
Автоморфизм.
Ну, послойные, значит, что они над базой. Потому что диаграмма коммутативна. Это автоморфизм, два от умножения в базу. Ну,
точки в одном слое мы подействовали, они проецируются в одну точку.
Я просто пытаюсь понять, когда это может отличаться, ну, в каком смысле это может быть.
Когда нерегулярное накрытие.
Слово, кроме автоморфизм, то есть зачем еще одно?
Just transformation.
Да. Зачем использовать эту фразу вместо?
Just the way people call it. Maybe it's better to call it automorphism, group of the covering, but I don't know, just under terminology. Maybe there is some good reason, but I cannot tell. Yes, so algebraically, we have the short exact sequence. G modulo G double prime goes into the abelianization, G modulo G prime goes to 1. And here, G prime modulo G double prime. Yes. So we have this short exact sequence, and so this group is Z in our case because this is the abelianization. G is complement of the fundamental group of the complement of the node, so its abelianization is Z. And so this homomorphism splits because Z is a free group. And then this T, which is the generator here, it just acts here by conjugation. But if we start from an element of this kernel and conjugate it by T, then it stays inside of this kernel. And also it doesn't depend on the choice of the splitting, as it's easy to check, because if you, so suppose G is here and we want to conjugate G by T, or we can conjugate G by some other element T prime, given by another splitting. So here is also T, but if we fix a different splitting, then we will get a T prime. But the T prime is T times some C, where C goes to 1 in this abelianization. So C is an element of the commutator subgroup, so it comes from here. So I can write T times C. Well, it's better to write C times T. It's also possible to do. But then this is G conjugated by C and then conjugated by T. But G conjugated by C is G. Because this group is abelian. And we both G and C are here. So G conjugated by C is G. So this is the action by T from the algebraic viewpoint. Just by conjugation.
Как сплит по-русски?
Расщепление. Это точно последовательность, ну, она чисто алгебраическая, нет геометрического смысла, да?
в этой последовательности, да. Ну вот.
Ну, типа, ну там один, потом вот эта группа H1, а вот этот G по второй производной, то есть. Что такое?
I don't know a good geometric description of this sequence.
Можно в первый раз, то есть для вот фактора G по G' есть интерпретация, это вот она, вот это вот циклическое накрытие. А дальше мы G' по своему штриху факторизуем. Эта ситуация чем-то отличается? То есть там не будет следующего.
Well, okay, so this is no. This is the homology of the curve. This is something more complicated. This is just the abelianization or the homology of the
Ну, Бог с ним доказали, да,
complement. So this was just a definition. Now, now we want to, what do we want? We want to show that we are still using lambda 2. We will always use lambda 2. But we are given these two knots, and we want to prove that they are conjugate modular the second commutator subgroup. This is all that we want to do. So we can look at their, so here maybe Q what was Qi and Qi minus 1. Okay, so we have their classes Qi and Qi minus 1 in G, and also in G modulo the second commutator subgroup. And we want to show that they are conjugate. Let us call them A and B. Of course, to have this as classes, we need to fix some tails going to the base point. Maybe I can erase this.
То есть та же самая верность появится.
Yes. Okay, so I want to find G such that A conjugated by G equals B. So I don't know if there exists such a G. But let me rewrite this equation. Let me write A inverse, then I write A conjugated by G equals A inverse B. Now this belongs to the commutator subgroup, because A and B have the same abelianization. This both knots have linking number 1 with KT, so they have the same they both go to 1 in the abelianization, and then their difference belongs to the commutator subgroup. Their quotient fraction. So let me call this C. Let me call this C. And this I can rewrite. Just let me write A minus 1, G minus 1, AG equals C. And I can write this as G inverse conjugated by A times G equals C. Okay. Now it would be enough if I find such G just in the entire group G G capital. But I want to find this G in the commutator subgroup. So then C lies in the commutator subgroup and G lies in the commutator subgroup. And this is conjugation by A. And this is the same as conjugation by T, because I can choose the splitting so that T goes to A. So this is really this action by T. So I can rewrite the same equation in the additive notation as follows. T times minus G plus G equals, this multiplication becomes plus, this inverse becomes minus, and conjugation becomes action by T. So I want to solve this equation in the sense that I want to find a G such that this equation is satisfied. Well, I can write it. So this is 1 minus T times G equals C. And I want to find the G which satisfies this equation. Okay, so I have this module yes, so this equation, this conjugation was supposed to be modular G prime prime. So when I write this, I already assume that we take the quotient of everything by G prime prime. So we actually live in this quotient, and this is an equation in this quotient. Now, should I explain in more detail? So this was supposed to be, yes, I wrote it here. I looked at them in this, their classes in this quotient, and this was A and B. So this was, everything what I said was correct. This was going on in this quotient. And here we have that both G and C lie actually in G prime modular G prime prime. Well, okay, here I could say also G prime prime. Just because C is A inverse B, and A and B have the same abelianization, so they this C lives here. And G lives here just because I claim that we can find it inside of this subgroup. But this quotient has this geometric interpretation. So I can write it like this. I have this knowledge group of the infinite cyclic covering, and I have the homomorphism from this group to itself, which is multiplication by 1 minus T. Or action by 1 minus T. And the final lemma says that this is an isomorphism. If we prove this lemma, then we are finished, because well, if this is an isomorphism and we take C here, then we can divide it by 1 minus T, so we can find an element G such that G times 1 minus T is C. It is enough to show actually that it is surjective. And then this equation can be solved. So let me prove this now. Okay? maybe I can just do it here. So there is a there is a log exact sequence which includes that homomorphism. Namely, I can look at the short coefficient sequence, which is, I take my ring and I take the multiplication by 1 minus t. So this is injective, and here the quotient, so if the quotient is the co-kernel of this map is obtained by equating t and 1, t equals 1. Well, if t equals 1, then we just get z. So we have such a short coefficient sequence of modules over this ring of round polynomials. That is also a module just with trivial action of t.
А какое рассуждение было, почему именно z будет фактор?
Because this should be the co-kernel of this map, and to find its co-kernel I must equate t and 1, because this was 1 minus t.
Я понял.
1 minus t equals 0, better to say. Yes? I take the quotient by the image, it means that I take the quotient by this ideal. And this means that t equals 1, and if t equals 1, then I get that. So, corresponding to this short exact sequence of coefficients, we have a long exact sequence of homology groups. So what is homology with coefficients in a module? Well, this is a module over the fundamental group. So we have the group ring of the fundamental group. Which is, well, it is a complicated group, but the organization of this group, I can write like this. So there is an organization, and the organization is this ring. So there is this homomorphism, and this makes this abelian groups also modules over a group ring of the fundamental group. Then we have the homology for modules with for modules over fundamental group, and this is just local homology. So maybe I should give the definition. So we have we can start with a chain complex. This is well known stuff, but maybe I should recall this. Well, it's better to take the chain complex of Well, so if I want modules over this fundamental group, then I should take the universal cover. But actually we need just modules over this homology, so it corresponds precisely to taking the infinite cyclic cover. So this is already a module over the Laurent polynomials, because just T acts on this infinite cyclic cover by translations. And now if I have any module M over this ring, then I can take a tensor product with M over this ring. And then I take the homologies. So there is a chain complex, and I take the homology of this chain complex. And this is by definition called the homology of this S3 minus KT with coefficients in so in the usual definition, M is a module over the group ring of the fundamental group, and this is the universal cover. But we can also do it with infinite cyclic cover if M is a module over the group ring of the homology. So this is defined that well, I don't know if I should explain the geometric meaning of this local homology. Maybe not. But this short coefficient sequence gives a long exact sequence of homology groups.
Я что-то забыл, зачем все эти заморочки? Это же матрица этого отображения, это же и есть матрица представления узла, да? Или нет?
Что значит представление узла?
Ну, матрица вот этого гомоморфизма, умножения на 1 минус t. Это матрица представления модуля, вот этого, определитель, который полином Александера или нет?
No, I don't think that, well, first of all, this is a wild knot, and it doesn't have the Alexandria polynomial.
Ну, вообще,
But
да.
if it is a tame knot, then I don't think that this is why is this? I don't understand. So you are saying that the matrix of this map is related to the Alexandria polynomial? One minus t? Why? Maybe you're right, but I cannot say at the moment, but in our case it is a valid knot, and we don't have, it doesn't have any Alexandrian polynomial. It's an infinite matrix, which doesn't have determinant because it's infinite. So there is some problem with that. Okay, so we get the following long exact sequence. H1 has 3 minus kt with coefficients let me call this lambda because it's too long to write all the time. With coefficients in lambda, then 1 minus t h1 plus 3 minus kt with coefficients in lambda, and then h0, h1 is 3 minus kt with coefficients in z.
Простите, я потерялся. Что такое лямбда?
It is just lambda is the ring of Laurent polynomials. Okay? It's just too long to write it all the time. And then h0 of h3 minus kt lambda. And I think I should write here one more term. H2 is 3 minus kt z. Okay, so this is the usual homology. The action of t is trivial. It means that this homology with local coefficients is actually the usual homology. And similarly here. But this homology group is isomorphic by the Alexander duality to h0 of kt. No, h0. And this is reduced. This is 0. So this is just 0. This is the Alexander duality. So this is 0. This group is not 0, but okay, but I claim that this homomorphism is just what we want here, because if we have lambda here, I mean our ring of Laurent polynomials. If you just look at the definition, you can see that we are taking the chain complex of this infinite cyclic cover, and then we take the tensor product with lambda over lambda. But this is it means doing nothing. This is the same as the original chain complex. So the homology of this is just the homology of this, which is the homology of the infinite cyclic cover. This can be explained geometrically, but I don't know if I should do it now. So this is the homomorphism that we are interested in. We already proved that it is injective, but we actually are more interested to prove that it is surjective. So to prove that it is surjective, we want to look at this map. So this is h0 of S3 minus kt, the infinite cyclic covering z, if you want. So this is the usual homology of the complement to the knot, and this is the usual homology of its infinite cyclic covering. And what is this map? this map is the connecting homomorphism. Well, if you write the long exact sequence of homology groups corresponding to a short sequence of coefficients, then there is a standard way to define this connecting homomorphism. If you apply it to this situation, then you get the following description of this delta. So delta of some, if we take some cycle Z, so its homology class is in this group. And then its image will be a zero cycle W, represented by a zero cycle W, if the following holds. So in these terms, Z is just a cycle as a complement to the knot, and we can represent it as the image of a cycle in the infinite cyclic covering. So we have complement to the knot, and we have the infinite cyclic covering. And here we have a cycle, and we can represent it as the image of some chain here. Let me go see. So we can always lift a chain to another chain, because this is a covering. But this C, of course, it is not a cycle anymore. So it has boundary, and so I want to write here that C equals 1 minus T times W. So the boundary of C. The boundary of C, well, let me draw a picture. We have our knot, wild knot, and we have some cycle Z. And now if we look at the infinite cyclic covering, then above this cycle there is some chain. Maybe I should call it that tilde. And it has boundary. Well, this boundary, it has to cancel when you project it down. So it means that, well, if these are 2 points like in this picture, then they are just the same point but in different layers of this, different, how do you say, sheets, in different sheets of this color. So we just lifted this point to the next sheet. And so it means that this boundary is actually visible by 1 minus T. Well, one of them, if you take the boundary, one comes with plus and another with minus. But also this comes with a T because it is from the next sheet. And so this point is W actually. And this is how the connecting homomorphism works. It associates to this one-dimensional cycle in the bottom the zero-dimensional cycle, which is this point. And you can see this from the description of this connecting homomorphism.
Sorry.
Huh?
Sorry, it's late and I'm hungry and I have to leave if I want to have something to eat.
Okay, goodbye. But it's almost done because this group is Z zero-dimensional homology, and this group is Z, one-dimensional homology of the complement. We want to find this map from Z to Z. And as you see from this description, this is an isomorphism. So if we start from a non-trivial cycle here, we get just a point in the infinite cyclic covering which generates a zero-dimensional homology. So this is an isomorphism, and so this means that this map is zero, and so we get that this is an isomorphism, which is what we wanted to prove. So the proof is finished, and this was the second proof of the lemma.
Попроще, да?
Yes, this is the simplest proof in some sense, but it is simple if you assume this thing
Я
is known.
что-то упустил. Какую мы последовательность умножили тензорно на последовательность модулей? Точную последовательность пары или чего?
We take the chain complex of the infinite cyclic covering, and it is a module over lambda, and then we can take the tensor product with any other module over lambda.
Что такое лямбда?
Laurent polynomials.
А, то же самое, понял, да?
А можно сейчас отойти на минуту?
Okay, maybe I should finish because people are tired, and I think it's time to finish. So thank you everyone who survived this. До свидания.